like we say right here, we had two theorems, and we just use them to evaluate double integrals. So that's very analogous to double integrals, right? We also had two methods. The projection method, or you can say the Fubini's theorem. And now for the second method, we have the use of spherical corners. This is quite similar to polar corners, but we cannot use polar corners right here because now we are working with objects in three dimensions, and polar corners can only be used in two dimensions. So this time we need something similar, and we had spherical corners. So we had two methods, and you had a note, you can easily read the whole thing, and you will see that nothing so new right here. Everything is so consistent with what we already saw in double integrals. And again, the two methods are based on two theorems. The first one is the Fubini's theorem, and the second one is the use of spherical corners based on two theorems. And in class, I'm not going to prove anything because usually it requires time, and you will see that it might be too technical. But it does not mean that you cannot understand the proof. If you read the textbook by James, you will see, yeah, he used many pictures, many images to show you the idea, maybe just the idea of the proof. And it might be helpful if you spend some time with the textbook and see why we had these formulas. If you don't understand the proof, you can send me a message. All right, so let's go to what we have in this note. Now let's consider the first method, the projection method. All right, so now you can see this time we have an object in 3 dimensions, not 2 dimensions like double integrals. We have an object in 3 dimensions, and the function we have now is a function of 3 variables. So just imagine that this is the density function. So we have 3 variables. And now we would like to evaluate the triple integral of the function f over the solid E. Now, the projection method tells you that we can get this by evaluating a very simple integrated integral like this one. However, first we need to determine which setting we have for the solid. So similar to double integrals, we can use setting 1 or setting 2, but right here you can see we have not only 2 but 3 settings, setting 1, and then if you read the note, you can see the domain we had, the solid we had, it may be given in setting 2, or it may be given in setting 3. So we had 3 settings right here, not 2, just because now we had 3 planes to project the solid on. For example, if you consider setting 1, you can say in order to use setting 1, first you need to consider the projection of the solid E onto the plane X or Y. So that's setting 1. However, now you still have the plane S or Z. So if you project the whole solid onto the plane S or Z, if you go for that, then we have setting 2. And now you still have the plane Y or Z. If you project the whole solid onto Y or Z, then we have setting 3. So for double integrals, we can project onto OS setting 1 or onto OY setting 2. So because we have only 2 axes, now we have 3 settings for triple integers, just because we have 3 planes, SOY, SOZ, or YOZ. All right, so yeah, so let's focus on setting 1 first. So right here, I just try to show you how to apply the projection method correctly. So that's the main focus right here. All right, so it's very simple, and it's quite similar to the projection method we already saw in double integrals. Now, let's say now we have a solid E. So the first thing you do, if you consider the projection method, is to consider the projection of E onto the plane SOY. So you get the domain D. So we have D right here. It's a, you can read this, it's a the projection of E onto the plane OSY. So that's the first thing you need to determine. And then you need to know the 2 functions, Z1 of SY and Z2 of SY. And they are from the lower surface and the upper surface of the solid E. In order to see the lower and the upper surface, you need to go up. So you go like this. You go up in the OZ direction, you go up like this. The first surface you encounter is exactly the lower surface. And then you need to find an equation of that surface in the form Z equals something of SY, and something of SY right here is exactly the function Z1 of SY. And then you go inside the solid until you go out. And if you go out from the surface of equation Z equals Z2 of SY, then Z2 of SY is exactly the upper limit we put in here. And then we have this integrated in mathematics. We call this an integrated integral. We had this integrated integral, and it's just, you know, doing some computation, and you get the answer. All right, so in summary, in order to evaluate a triple integral using the projection method, given that the domain in setting 1, then you only need to know 3 things. You need to know the domain D, which is the projection of A onto OSY. You need to know the function Z1 of SY, which is from the lower surface. And you need to know the function Z2 of SY, which is from the upper surface. If you can determine these 3 things, everything now is just, you know, a matter of some computation and get the answer. All right, so you can see one example right here. Yeah, so just follow exactly what we have in here. So in this example, we need to get the triple integral of the function s plus y plus z. This is the function f, and the solid E is the solid bounded by the paraboloid. You see it's right here, and the plane z equals 4. So everything between the 2 surfaces right here would be the solid E. Now you can see the first thing I immediately consider right here is the setting we have, the 3 things we have. So first I need to know the projection D. D is just the projection of the whole E onto SOY. So I think you can see that, no problem, right? So the projection of the whole E onto SOY is exactly this of radius 2 right here. So that's the projection, no problem right here, right? And then I need to know the function Z1 of SY. So I need to know the lower surface. In order to see the lower surface, we need to go like this. We go in the OZ direction, we go up. And you can see the first surface we encounter always the paraboloid, right? Z equals S squared plus Y squared. And we need to get something of SY from that, and it's obviously S squared plus Y squared right here, and this is exactly the function Z1 of SY. So you know Z1 of SY right here. And then you go inside E until you go out, and you can see always we go out from the plane Z equals 4, and we need to get an equation of the form Z equals something of SY. And something of SY right here in this example is exactly the constant 4. So 4 is the function Z2 SY. So we put that in here. And remember that right here we had D, we see the projection, and now we get this one. And we know exactly what we need to do now, right? So just focus on the inside integral first. Get the inside first. Right here we integrate with respect to Z. So S, Y, they are constants. So in order to evaluate this with respect to Z, we get an antiderivative with respect to Z, and we insert the two limits. Z equals x squared plus y squared and z equals 4 into this, and we get this. So let's say what we have for everything inside the square brackets, right? With respect to Z right here. And now we still have the double integral outside. So you can see, in order to evaluate a triple integral, we cannot ignore double integrals because basically we need to go back to double integrals when we use the projection method. So still have the double integral, and we need to evaluate it. But let's say an O10, right? We can use polar corners to get the answer. But in this note, you can see we can save time a bit because basically when you integrate this function over the disk, you get 0. I also gave you y in this note. You can see basically they say an odd function with respect to s, and the domain is symmetric about the OY axis. So this is 0. So they say an O10, right? And they say also 0 because they say all with respect to y. Domain is symmetric about the OS axis. Therefore, we save time a bit when we consider this. So we only need to focus on this one. So right here, we can continue with this one only. And using polar corners, we get the answer. So this is one example. All right, so any questions right here? So I think I need to put a remark right here. So remark. Similar to this remark, in in double integrals, this time I would like to consider the case, I would say the simplest case when we have a rectangular solid. What happens then? So let's say if E is like this, so it's a rectangular solid. So let me try to show you a picture right here. So we have S, Y, Z. So we have some rectangular parts right here. See, that's so yeah. So assume that you have AB right here, CD, and right here you have EK. This is a rectangular solid, or you can say rectangular parts. Then, what do we have for this triple integral? Now, pay attention to the notation we have right here. We have dv. When you see dv, you would know that we have a triple integral. Yeah. So dA double integral, dv triple integral, and also we had 3 integral sides right here, dv for triple integrals. Then we have, now we have this one. So EK dz C D dy A B ds f s y z. If you would like, you can put some square brackets right here to make it better. So you have like this if you want. Yeah. So you have something like this. So what I'm trying to do is to show you that we had something very similar to this when we consider double integrals. So let me try to show you why we had this. Yeah. So why we had this formula? The answer is we just applied the projection method. Exactly what we are discussing right here. In setting 1, now let's say, so y, so the answer is, let's apply the projection setting 1. Now let's say, all right, so in order to apply the projection method, in the first setting, you need to know 3 things, right? So you need to know first the domain D, and then you need to know the function z1 of sy, and then you need to know the function z2. What do we have for D? In our example right here, D is the projection of the whole solid onto the plane SOY. And you would immediately see that we get this one. So maybe I just put it in 3 dimensions first. Yeah, you would see we get the projection right here. This is exactly D. And if you just draw it in 2 dimensions, then this is exactly what we have. So SY, and we get some rectangle right here. Let's say A, B, C, D. Yeah. All right, so done for D, right? Now let's see what do we have for the function z1 of sy. Is it from the lower surface? So we need to go up, go like this. Or you can say we look at the surface from below, right? We go up the first surface. We always meet when we encounter E is always from the base of the rectangular parts right here, right? So we always meet this surface first. So this is definitely the lower surface. And what next? The next thing we need to do is to get an equation of this surface in the form z equals something of sy. So what do we have for this? What's in the equation of this surface, the lower surface, in the form z equals something of sy? And the answer should be z equals E, right? Because any point on this surface, the z component always equals to E, right? So the answer should be E right here. Do you see that any point on this surface, the z component is always the constant E, right? This is a constant. So we know that this is exactly the function z1 of sy. And now, any problem with this one? So let's write E right here. Now we need to know the function z2 sy, and again we need to determine the upper surface. And in order to see the upper surface, we need to go up and continue going inside until we go outside. And we can see that we always go out our solid from the plane z. Let me look at the notation k, right? So the upper surface is the plane z equal k. We need to get an equation in the form z equals something of sy, and in our simple example, f something of sy is exactly the constant k. So k right here is exactly the function z2 sy. Right, so we know now, yeah, right here we had k. All right, so we know the setting now, so we just apply the projection method right here. And let's see what do we get. So from here we get, if we apply what we get right here is, now you have the domain D, we see the rectangle right here. So we have A, B, C, D, this is Y, this is S. And inside we have a definite integral with respect to Z from the function Z1 to the function Z2. And Z1 is E, Z2 is K, so we have E to K. And inside we had a function f of sy z, and this is dz, and outside we had dA. dA right here is with respect to s and y. All right, so we had this one, right? I think, yeah, so maybe the order right here is not exactly what I want. I think I need to correct this. Let me correct this one. So the order right here is all right, no problem with this one. This is correct, but it's not exactly what I would like to do at now. So let me try to rewrite this. This is still correct, but let me discuss this later. But at the moment, I think I should write the z inside. So let me erase this one and rewrite it. But I would like to say this is still all right, no problem. But let me discuss this later. And you may guess what I'm going to tell you is, when you have a rectangular solid, you can change the order as you wish. You can write ds, dy, dz like this one. It's still correct. Or if you would like, you can put dz first and ds, dy later. It's still correct. So that's exactly my aim. So, but when I wrote this, not exactly what I would like to do now. So let me erase this one and just write like this. So we had 3, but I would like to have the z right here. So we have f of sy dz, and this is ek because z is from e to k. And let's say right here we have y, so we have c, d, dy, and right here we have a, b, ds. Yeah, so this is what I would like to show you first. Yeah. So why do we have this formula? The answer is, now let's say just apply the projection method, and now you can see why we have, right? So we are at this formula, right? We just apply the projection method in setting 1, and we go in here. And from here, I think you can see why we had this formula. Yeah. So let's continue with this one. And now we have, so let's say let's say this is, let me put something right here, some number here. Let's say this is m. All right. So m is this integral. And remember that m right here should depend also on s and y, because when you integrate with respect to z, s and y right here are constants. So in the end, you have m, but m is a function of s and y. But let me just write m right here. And now we have this double integral, right, of m dA. And then right here, we need to evaluate this triple integral, sorry, this double integral also, and you know we can apply the projection method. Like we did many times before, right? This is a double integral, apply the projection method. Let's say we apply in setting 1. Now let's say, I think, yeah, so let's say we apply in setting 2. Setting 1 and setting 2 is not so important, right? So from here, if we would like to get this one, then we apply setting 2 right here, right? So setting 2 or setting 1, let me write both. Then you get something like A, B, C, D, M. Now, if you apply setting 2 right here, you get dy, ds, right? If you apply setting 1 right here, you get ds, dy. Is that right? Because this is a rectangular domain, so from here, we have that this is equal to this one. This is also equal to this one. You can change the order if you wish. So exactly what I wrote from the beginning right here. Any order, no problem. Just, you know, depending on the setting you would like to consider. Because right here we have a rectangular domain, right? So you can see, now let's say I determine writing this for this, then you can see we have exactly what I wrote right here, right? So the inside is exactly m, and then we have dy, and then outside we have ds. However, if you consider this, then you see that we have dz and then ds, dy. So you can see that we can change the order if we have a rectangular domain, a rectangular solid. So from this example, you have any question about this? So what I have shown you is why we had this formula, and the answer is we had this formula because we just applied the projection method. And in the end, we will see this one. But maybe it's better to have a remark right here. So let me put a remark right here very quickly. So a helpful remark. Now, if we have a rectangular solid, like this, let's say this is E, then when you integrate any function f over E, you can draw it in any order. So let me show you. Let's say I would like to have the order right here, ds and then dz and then dy. Let's say I would like to have this order, no problem. Now let's say what we need to write in here. So this is ds, right? So s is between a and b, so you need to write a, b right here, because this is with respect to s. And then we have dz, So Z is between E and K. So you need to write E to K right here because we had dz. And the last one, dy, is between C, D. So we have C, D. And of course, inside right here, we have the function f of s, y, z. Yeah, so this is exactly what we have. And this is the correct formula. Let's say you would like to have a different order. Let's say this time you would like to have dy, dz, and then ds. No problem. You can write this one as it's still equal right here. No problem. So if this is dy, then you should write cd right here. So we have cd or dy, right? Yeah, and then we had dz. So it should be from ek. So we have ek. And the last one, ds, should be from ab. And then obviously inside we had a function. All right, so if you would like to go for this, it's still all right. Yeah, we have many different orders. I think we have 3 factorial, so we have 6 different orders. So you can go in any order. The only thing you need to pay attention to is the domain we have for each variable, right? So if we had ds right here, it should be from A to B, not from C to D or E to K. Yeah, that's the only thing you need to pay attention to. Is that all right with this remark? You have any concern about this remark? And this is quite similar to what we already saw in double integrals. All right, so yeah, so the projection method. And one thing I would like to tell you, maybe it's helpful. So the last thing I would like to tell you about this remark is the question, how can we change the order like this for a rectangular solid? How can we just write in any order like this? If we have a rectangular solid, the answer is just because we can apply the projection method in different settings. If we apply setting 1, then basically you get some order corresponding to that setting. If you apply setting 2, then you have some orders corresponding to that. If you apply setting 3, you have some orders corresponding to that. That's why we had this, because for whatever setting you apply, we still have the same thing, right? Because the left-hand side is still the integral of the function f over the solid E, right? So we still had the same thing. All right, so that's a remark we have right here. So you may ask the question, if we don't have a rectangular solid, if the solid E is not a rectangular solid, what would we do? The answer is we just focus on the solid and see which setting is suitable for the solid we have. In this example, you can see the solid we have here. This is not a rectangular solid, right? But we can see that a solid like this is perfect for setting 1, right? When we can easily find the projection onto S or Y and the lower the upper surfaces. However, if you are given some solid, let's say suitable for setting 2 or setting 3, then you just go for that. Yeah, for those. However, good news is in this course, we mostly focus on setting 1 for triple integrals. So for triple integrals, for the projection method, you will see problems given in setting 1 only. Most of the time, we rarely need to consider setting 2 or setting 3. Yeah, for a zero domain. So that's the good news. let me say it again. If you are given a solid, a zero solid, and we need to apply the projection method. Usually, it's given in setting 1 already, so you just apply setting 1. Find the projection onto the plane x or y, find the two functions z1, z2, and go for this formula. So most of the time, we just focus on setting 1 in 3.0s for the projection method. All right, so let me try to end the whole note by going to the second method, the use of spherical corners. And again, for the second method, we need to employ a term. And in class, I'm not going to prove the term. So let me try to explain it a bit. So how to apply this term? So assume that you would like to integrate a function f over some solid E. In this term, it says that we can turn this into a new 3.0. So the right-hand side is still a 3.0. You can say this is dv, let's say a 3.0. The idea is we can turn this O into this new 3.0. However, the new one, you can see it's in rho, phi, and theta. And we hope that the new integral right here with the new function and the new domain f, we hope that this is similar than the original one. So that's the idea we have right here for this term. Now let's see how to use this term. It's very simple. You can say the only thing you need to know when you apply this term is the domain f. The domain f is the domain we have for rho, phi, and theta in spherical corners. So I hope that you remember what spherical corners are. You can read or go back to the assignment we have. So the only thing we need to know is the domain f. You only need to know f. F is the domain we have for rho, phi, theta, and they are in spherical corners. And then you put that in here. We apply this formula, and we can evaluate this guy. So let's see how to write it correctly. So you can see right here we had a function f of x, y, z. X, y, z are Cartesian corners. And if you remember the relation we have between Cartesian corners and spherical corners, then you would immediately write down this. So S is exactly rho cosine phi sine theta, Y is rho sine phi sine theta, and Z is rho cosine theta. So basically, the term right here is exactly f of x, y, z written in spherical corners. And then right here we have dv. You can imagine that dv right here is exactly ds, dy, dz. And we have the following formula. We see the key thing in this theorem, but I'm not going to prove that. So we had this. Yeah. So we had this formula. So that's why we had the term rho squared sine theta right here. So dv right here, you would think of this as d rho, d phi, d theta. And dv right here is ds, dy, dz. And in fact, we can prove this change. So that's why we have this. And in mathematics, we call this one the Jacobian of the change from Cartesian corners to spherical corners. So let me write down that name. You don't need to remember that also. So this guy, maybe I do something a little bit fancy right here. So no, yeah, still do that. So this is the Jacobian in the change from Cartesians to spherical coordinates. This right here is the guy you see right here, rho squared psi of theta. So when you hear someone saying Jacobian, you know exactly rho squared psi of theta. And if you remember, what we have in double integrals, so let me remind you also, FSYDA is FR cosine phi, R psi phi, R dA. Then this guy is also in mathematics. We also call this the Jacobian interchange from Cartesian coordinates to polar coordinates. So we had the same name, Jacobian. So rho squared psi theta right here is the Jacobian interchange from Cartesian coordinates to spherical coordinates. Don't need to remember this. So also have an example right here. You can see, let me go through this example. So right here, we need to integrate the function z over a solid E. The solid E we have is anything inside the hemisphere of the radius 3, right? Only a hemisphere you see right here. Now you can see that this is a spherical domain, so the best way to get the answer is to apply this formula. So the only thing we need to know in order to get the answer is to get the domain F. The domain F is the domain we have for rho, phi, and theta, and rho, phi, theta are spherical coordinates. So this is the range we have, and I hope that you know why we had this. So last time we already did some questions like this, right? So determine the range we have for these three rho, phi, theta. All right, so then for F, so in spherical coordinates, let's see what we have for F. So phi is between 0 and 2 pi. Why do we have this? Remember that in order to find the range of phi, we only need to find the projection of the whole solid onto the plane SOY and look at the range in polar coordinates of the projection. The projection in this example is the whole this, so phi should be from 0 to 2 pi. If you want, you can write from minus pi to pi, still the same. Theta is between 0 and pi over 2, just because everything in here is above the plane SOY. And the last one, rho, is between 0 and 3. Everything in here should be inside the sphere of radius 3. So we have this one. And now that's this is the main thing, and we are done. And now we only need to put everything right here into our formula. Yeah. So let's see what do we have in this example. Look at the function first. The function we have is only z. In general, we have a function f of s, y, z. But in this example, we have only z. We had no problem with that, right? So z in spherical coordinates, z is rho cosine of theta. We need to remember this formula. So z is rho cosine of theta. And don't forget the Jacobian we have right here. So the Jacobian is rho squared psi of theta. And now we need to consider this triple integral. This is still a triple integral, right? So similar to what we have right here in double integrals. We use polar coordinates, but we still get a double integral. We need to handle this also. And right here, we still have a triple integral. But the advantage right here is that the domain F we have right here, you can see it's a rectangular domain, right? Let me try to draw a picture of the domain F right here so that you can see. So we still have a 3.0, but the main thing right here is that the new function and the new domain is basically the new domain right here is very good because it's a rectangular domain, right? Do you see that? So this is in this example we have 0, 3 for rho. For theta we have from 0 to pi over 2. And right here we have 0 to 2 pi. Yeah. Sorry. It should be 0 right here. So yeah, just so you the idea. Maybe it's not a nice picture. All right, so this is a rectangular domain, right? So you can change any order you want, no problem with the order. So you may write d rho, d theta, d phi like this one. Or if you would like, you can write d theta first and then d phi and then d rho, or you can write d theta, d rho, d phi, any order. We have 6 different orders, right? So no problem with that. If you write d rho, d theta, d phi, you need to pay attention to the domain, the corresponding domains we have for it. All right, so this is correct because I consider this order. So the domains, yeah. And now doing some computation, get the answer. So that's what we have. I think right here, I would like to put another remark so that you can save time when you see something like this. What I mean is, so put another remark right here. And I think this is the last thing we had today. Assume that you have a rectangular solid E. So let's say so maybe I use too many if. So let's write assume that E is a rectangular solid. Then if we integrate a function over E and assume that the function is given in this form, let's say you have f1 of s, f2 of y, f3 of z. This is a very special type of functions, but assume that you had that. So assume that you have a function f of x, y, z, and it can be written in this form. So basically, this is a very special function, and in general, we may not have this, but if we have this type of functions, like in this example, then we have the following formula. So assume that you integrate a function like this, when you can separate s, y, z into 3 separate functions like this one, then you can immediately get the answer in this way. So AB f1 of s, CD f2 y, EK f3 of z, dz. Yeah. So you can save time why do we have this formula? The answer is you just do it slowly and then you get this one. Yeah, no problem with this. You just first from here you go into this. First from here you go into this one. You go into this one. And then you will see that what we get is exactly this. So the answer to this question, get it slowly. All right, so you can save time. If you had this, maybe I put an example right here. So example. Now evaluate. Let's say x squared y plus maybe a different number. So where e is now the answer is now I would like to point out that this is the number 2, not z. If it's a z, it's not exactly what we have right here. It's the number 2. All right, so z minus 3 dv. Now you can see that this is a very special function because s, y, and z they are separate into 3 different terms, right? So exactly in the form we have now, you know exactly what we have now, right? So this is exactly, you can immediately get the answer like this. Immediately see the answer like this. Yeah, and then you use your calculator. And you get the answer. All right, so this is the end of what we have for today. Any questions? All right, so if you don't have any questions, maybe we have a break. In the meantime, you can try with this. Remember that the due time is not so far from now. We have only 1 day, so maybe save time by getting it done right here in class. So with questions for practice, triple integers. For the first 2 questions, I tried to remind you about spherical corners. Yeah, you may forget how to set it right, so it's time to record this. And then from question number 3 up to the end, we have triple integers. Question number 3 and 4, the 2 questions 3 and 4, they are like tutorial questions. When you have the instructions, and the instructions you see right here in question 3 or 4 are exactly what we have been discussing so far, right? Nothing new right here. So you don't need these instructions. They are just from what we have right here. All right, so now we have a break, and you can try to find the answers to these questions. All right. Now let's try to find the answers to some questions in this assignment. Now let's see question number 1. Here you can find the answer. So in this question, we need to give the setting. We have for rho phi theta. The domain we have is the solid inside this hemisphere. You can see first the range of phi. So let me try to give you the answer to this question. First, the range of phi is, for my question, from 0 to 2 pi, because in order to find this, we only need to look at the projection of V onto OSY. Then you get this one. And then you look at the range in polar coordinates. It will give you the answer to the range of phi. You can write from minus pi to pi, no problem. But let me write from 0 to 2 pi. Now let's see what do we have for the range of theta. Theta is the angle between OZ and OM, right? When you focus on a point M, you would like to know theta of M. You look at the angle between the vector OZ and the vector OM, and you can see for any point M inside our hemisphere, the angle is always somewhere between pi over 2 and pi. So that's what we have for the range of theta. Maybe I give you a picture for this one. So SYZ, it can be pi over 2, that's the minimum if we look at a point like this one, right on the plane OSY, then the angle we have for this is exactly pi over 2. And let's say the minimum we can have, and the maximum we can have is pi. If you look at a point somewhere here, then the angle we have in this case is exactly pi. And if you look at another point somewhere else in between inside this, then you get somewhere between pi over 2 and pi. Yeah. All right, so minimum is pi over 2 and maximum is pi for theta. The last one, rho, obviously it can be 0 and can be close to 0, but it should be less than the number 4 for my question because the radius is 4. So this is the answer to my question 1. Question number 2 is quite similar, so I skip this one. Similar. Question number 3. So this is a tutorial question, so we just fill out this instructional process until we go to the end. Yeah. So question number 3, we have this 3.0. We would like to get this over the solid E. E is bounded by the plane gt2 and the paraboloid gt6 x squared plus 6y squared. Obviously, we need the projection method. And in order to use the projection method, we need to know three things. We need to know the domain D, we see the projection onto the plane SOY. And we need to know the function Z1 and Z2. They are from lower and upper surfaces. What do we have for D in my question? So we need to find the projection, right? So let me try to give you the answer to this question. So question number 3, I say that what we have in this question, a paraboloid, and then we have a plane, right? We had the paraboloid right here with the of equation. Sorry. 6 s squared plus 6 y squared. This is the paraboloid we have. And then we had the plane z equal 3 for my question. And now we can see the solid E is below the plane and above the paraboloid. So everything inside here would be E in our question. And we are going to use the projection method. So the first thing we need to do is to get the setting. So first, what do we have for D? It's the projection of the whole solid E onto the plane OSY. So we can easily see that the projection is a disk, right? Yeah, maybe it's not a good picture, but you can get the idea. So the projection so this is D, and we can easily find D, right? Because we know the equation of the paraboloid and the equation of the plane. We can only we only need to put them together, and we get, so put them together. This is the paraboloid. This is the plane. Put them together, we get this one. So we know that the one we see right here, the equation we see right here is exactly the equation of the boundary of the domain D. So this is only the boundary of D. So you know that D is anything inside this. So we know that what we have for D should be any point inside the circle. This is an equation of a circle, right? The circle we have is exactly this one. Yeah, we can draw like this or like this. They are the same. So the answer to this question is 3 over 6 with 1/2, right? Now, what do we have for the function z1 of sy? It's from the lower surface, and we can immediately see that if we go up, we always meet the paraboloid first. So this is the lower surface, and we know that an equation is z equals 6 s squared plus 6 y squared. So 6 s squared plus 6 y squared is the function z1 of sy. So write it here. This is from the lower surface, right? So this guy. And the upper surface is exactly the plane, right? And we know that it's the plane is equal to 3. So 3 should be the function z2. We have it right here. And now we know the setting. We need to consider this first in order to find the final answer. Consider this first. So we get this one. We need to evaluate this, right? Now we know the function z1 and z2, right? So this is with respect to z. So s, y, they are constants. So let's see what do we have in here. So we need to evaluate this guy first. Phi s is z. Remember that this is with respect to z, so sy just constant. An antiderivative is phi s z minus 3z squared, and z from 6s squared plus 6y squared to 3. So we have phi s minus yeah. All right, so that's what we have. The answer to this, right? Yeah, basically we have right here. And now it's only the inside interior. In order to find the answer to the question, we need to continue with the double interior. So now we put the whole thing we have right here into the double interior, and we need to find the answer right here. So let's see what do we have in the end. So from here, we know that the triple integral we have over E is exactly the double integral over the element D. The element D we have is right here, the disk. So the disk we have. And then inside we have the function right here. Is there anything inside? So this is the function we have. Phi s minus and dA for this. dA is dx dy. Now we need to find this double interior. One thing we can see is that this guy is disappeared, right? Because this is an odd function with respect to s, and the domain is obviously symmetric about the OY axis. So if you remember that property, you can see that this is 0 when we integrate over this. So I can immediately arrive at this. Because the first guy is disappeared, right? Is that right? And now polar coordinates right here, get the answer. So so maybe I write something right here in case you don't know what it is. So symmetric property. Let me write it better. So and let's say polar. And now we have from 0 to 2 pi, from 0 to the square root of 3 over 6. Inside we have minus 3 6 r squared. Don't forget the Jacobian r dr d phi. And now, remember that inside here we had no phi, so you know exactly what we had next, right? So we can draw like this: from 0 to 2 pi, the function 1. We don't see phi. It means the function is 1 for phi, so we had this. Let me put r in the beginning, so we have this. So I bring r up here. So we had this one, and then we can use and for my question, in the end, I get the answer right here, minus 9 pi. Yeah. Now let's go to question number 4. All right, so so in this question, we can use spherical coordinates to find to evaluate this triple integral. So the first thing we need to do is to get the domain F. The domain F is the domain we have for rho phi theta. So we can easily see that. So you can see having a picture like this is very helpful to get the range we have for rho phi theta. So I see that in this question for the domain E, the range we have for theta should be from 0 to pi, because we have below and also above the blend SOY. So theta can be anywhere between 0 and pi. For phi, it's obviously from minus pi over 2 to pi over 2, because when we purchase the whole E onto the blend SOY, we get the right half of the disk. So it should be from minus pi over 2 to pi over 2. Is that all right? So we are going to find the domain F for rho phi theta. And the last one for my question should be from 0 to 2, because the radius of the sphere is 2. So the setting is done, and the last thing we do is to get the final answer for this. So let me write it also. The final answer we have in our question first, let me rewrite the question. Is now we know F, right? And we can turn the whole thing into rho phi theta right here. This is F, and obviously right here we should have rho phi and theta. However, remember that when you consider S squared plus Y squared plus Z squared, you always get rho squared, right? Remember this formula. You can go back to the note. And don't forget rho squared psi of theta. This is the Jacobian. And right here we have dv, right? dv right here is d rho d phi d theta. We know f, right? So we can continue. And remember that this is a rectangular domain. So you can write in any order. You don't need to go for this order. This is d rho d phi d theta. If you don't like this, you can write d phi d theta d rho or any order. But you need to change the domains also. But anyway, so let me try to use the exact same order you see right here. If I use this order, then what we have right here is for d phi from 0 to pi, sorry, d theta, from d phi we have minus pi over 2, pi over 2, and for rho from 0 to 2, and the function we have is only this. And now you can see what next, right? The next thing we can draw is, you can see the function we have right here, is it in the form, like in this example. Maybe I go back very quickly to show you the idea we have. Yeah. Look at this remark. If the domain E is a rectangular domain, and if the function can be written in this way, when the variables are separate like this, so you can draw like this for the 3.0. All right, so let's go back to our question. And you can see the next thing I can immediately write out is, first, 0 pi for theta, so psi theta right here, and for phi minus pi over 2, pi over 2. Now you don't see any phi in this function. You should think of it as the function 1. So we have 1 right here for phi. And the last one, rho squared phi plus rho, d rho. Of course, you can write in any order. It doesn't matter because we have a product. So, you know, the order right here is not important. Right here, I write d theta first, and d phi, and then d rho. But you can see the order is not important. You can write in any order. And then we had the answer. Just use and we get the answer. Yeah, it's not a decimal number, but you can get something right here. So that's question number 4. Now let's go to question number 5. I think you can find the answer. Yeah, it's quite similar to question number 3, right? You have any problem with this one? I think we can skip question number 3. Very similar to question number 1.
Sir, can you please show me back the results of the question 1?
Question 1, right?
Yes, thank you. Thank you, sir.
So let's go to question number 6. Question number 6 is also similar to question number 5 or question number 3. But anyway, so let me try to show you the answer to question number 6. Now, so let's see what we have right here. So 6. Now you can see this is a triple zero, and the domain E is the domain bounded under the surface. This is what we call a paraboloid. So this is a paraboloid. You see it's right here, the upper surface. Yeah, it's right here. The zero surface is the paraboloid. And the domain E, the solid E is under this. And it's above the disk. The disk in this context is the disk in 2 dimensions in the plane X or Y. So let me try to show you to draw it again right here. So we have S, Y, Z. First, we have the paraboloid. So it's right here. Yeah, so maybe that's good enough. So Z is 1 plus 0.3 S squared plus Y squared. And then we have the disk S squared plus Y squared less than equal to 1.5 squared. So you should understand that the disk we are mentioning right here is the one in 2 dimensions right on the plane X or Y. So this guy is the disk. It's right on the plane X or Y. It's the disk of radius 1.5, center at the origin. So let's see what do we have for the solid E. Anything below the paraboloid, but above the disk. So you know exactly what it is, right? So it's right here. I'm not sure whether this is a good picture, but you can get it. But yeah, you can see it better in this picture. So let me try to remove this and try to draw like this. Yeah, maybe. Maybe we don't have this one. And let's try to use the 0 right here for this. All right, so yeah, so that's better. So now you can see the idea we have, right? So now it's very clear how to get the answer to the question. So we know the projection method is the best. So the projection what do we have for this? We need to know this. Now first, let's find the domain D. Is it the projection of the whole solid E onto the plane X or Y? What's it? The answer is obvious, right? When you project the whole solid onto X or Y, you get exactly the disk, right? You get exactly the disk. So the answer to the question is exactly the disk we have right here. So This is the projection of the whole solid onto SOY. Now let's see what do we have for the function z1 of sy. How to get it? Is it from the lower surface? So you need to go up. So you go like this. The first surface you meet when you encounter E, when you encounter the solid, is exactly the disk, right? You always meet the disk first. And you need to get an equation in the form z equals something of sy. And something of sy, obviously 0, because you can have any different thing right here, should be 0, because the equation of the disk is in the form z equals something should be z equals 0. Since it's on the plane SOY, right? So lower surface, and then we go inside until we go out, and we can see we always go out from the paraboloid, right? So the upper surface should be the paraboloid, and the equation in the form z equals something of sy is obviously from the equation of the paraboloid, we say 1 plus 0.3 x squared plus y squared for z. So we know everything now, so let's find the answer. So z1 and the function z2, right? We get them, right? And now let's find the answer to the question. So in the question, we need to evaluate the triple integral of the function 3.4z dv according to the projection method. First, we had the double integral right here. It's a over the domain D. And then inside, we have a definite integral. Right here, we had a function z1, which is 0. And up here, we had a function z2. And inside, of course, still the function f. And this should be dz. And outside, we had dA. The only way we can do now is, we can continue now is to get the inside first. Yeah, we had no other ways, right? In order to get this, we need to get the inside first with respect to z, and then we go out for the double integral. All right, so always like that, because this is not a rectangular solid, right? This is not a rectangular solid. If we have a rectangular solid, everything is simple, but this is not, so we need to go from inside first and until we get the answer. So now let's go from inside first. So I just rewrite this and don't do anything now, but I focus on the inside right here. So I focus on this one, and you can see an antiderivative of this one is this, and then we have dA outside, right? And now we try to get the inside. So we had 3.4 over 2, 1 plus 0.3, x squared plus y squared, all squared dA. Because when we insert 0, we get 0. Only for the upper limit, we get something right here. And now we can see that the next thing we do is obviously handle this double integral, and we use polar coordinates, and we can see that it's from 0 to 2 pi, 0 to 1.5 for the radius, 3.2, 4 over 2, 1 plus 0.3 r squared, all squared. Don't forget the Jacobian, dr, d phi. And now you know what next, right? So you can probably this and get the answer. So D phi, 1 for D phi because we don't see any phi inside. So and get the answer. For my question. So this the end of question number 6. Any concern about anything? We don't have any questions, so let's go to the next question. Now, question 7. Obviously, we need to use spherical corners. That's the best way to find the answer. So let's see how to find the answer to question 7. Now, the triple integral we have is 3z dv, right? And now we would like to use spherical corners. Now let's see how to get that. Right here we need to find the corresponding domain F for rho phi theta. And then inside we had 3z. When we transfer this into spherical corners, we get rho cosine theta. Remember the formula. But we don't forget the Jacobian rho square sine theta. And the last one, obviously, dv. dv right here is for rho phi theta. We still have a double integral. We have a new domain F and a new function. So we need to find the domain F, right? So we see that it's not so difficult if you remember the definitions. So you can see for theta, it should be from 0 to pi over 2 because every point in this domain E is above the plane SOY. So the angle between OZ and OM, M is the point, should be less than 90 degrees, right? So it should be less than pi over 2. So it can be 0. So theta should be between 0 and pi over 2. Now let's see what do we have for phi. In order to find the range of phi, you need to see what the projection of the whole solid E onto the plane SOY. You can see that if you imagine the projection we have of E onto SOY, you will see we get this one. You get this one for my question. The radius is 21. Let's see the projection of the whole E onto OSY. Do you see that? For my question, we get the disk of radius 21. And in polar corners, you know, the range is from 0 to 2 pi. If you want, you can write from minus pi to pi. And now the last thing we have, rho, it should be between the two radius, the radius of the smaller sphere and the radius of the bigger one. So 14, 21, that's what we have. Now, the next thing we do is get the answer, basically, because the domain F we have right here, they say a rectangular domain, right? Let me try to emphasize on this. So no problem with the order. You can immediately write down this like this. Maybe I save time further, maybe not. So let me write like this. Maybe I want to have this order, no problem, because you can do in any different. So let me go in this order, the row, and then we have inside the function called psi, right? Pay attention to the domains theta 0 pi by 2, pi 0 2 pi, rho 14, 21. And the next thing we can do is you can draw like this. Now this is the theta. We have some theta right here. You can draw like this. So I just pick up the number 3 inside, but if you don't want, you can leave it anywhere you want. So from 0 to 2 pi, we have no phi, we have 1 d phi. And the last one we have from 14, 21, rho cubed, d rho. Is that right? And now you get the answer. For my question, yeah, it's a quite big number. All right, so let's continue. So I think I skipped question 8. Question 9. So you know, for question 8, question 9, you need to have a picture in your mind, so that you can determine exactly what we need to do. These two questions are not so different. Maybe I go to question number 10. I think I have one thing to say about this question. Question number 10. Now let's see. So go to question 10. Now, in this question, I think I had something to say about this. What I'm going to say is we can use the symmetric property to save time, like we already saw in double integrals. Maybe I remind you what we had in double integrals, and then I show you what we had in this question. Now, so very quick review right here. So remember that if you integrate, now I should say, let's say double integral. If you integrate a function f of sy over some domain D, and if the domain D is symmetric about the OS axis, or you can say, if you don't like this, you can say the line y equals 0, because the line y equals 0 is exactly the x-axis. But this is not enough. We need one more thing. We need that the function f is odd with respect to y, then you can immediately say that the interior we have right here is 0. Yeah, so this is the property we have. Why do we have this property? The answer is it from the definition? The definition of this one is basically a limit of a sum. When you consider the sum, if the function and the domain had these properties, then when you look at the sum closely, you will see that we had two elements and they are opposites. Therefore, when you add them together, we get 0. So that's why we had this property. Or one way to think about this is when you remember that the same property we have for definite integrals in calculus 1. If you integrate an odd function over a symmetric domain, basically the interval from -a to a, we had 0, just because if you remember the definition, in definite integrals, basically we have an error, right? And if we add two opposite errors, we should get 0. So basically, all right. So this is a very helpful property because it saves time sometimes. Or we also had this the same thing if this the domain is symmetric about the OY axis. Or you can say the line s equals 0. But now you need f is odd with respect to s not y. If we had the exact two things like this, then you also have 0. Yeah. And now for triple integrals, we have a very similar thing. So let me write it. So this is just a reminder for double integrals. It's not new right here. So let's see what do we have if you consider triple integrals. Now, so we have the following f s y z dv e is the 0 if the domain E, the solid E, is symmetric about the plane S equals 0. Or you can say the plane Y or Z if you want. The same plane, right? Of course, not every solid has this property, but if somehow you have a solid with this property, it's a symmetric about the plane S equals 0, or you can say the plane Y or Z. But this is not enough. We also need that the function f is odd respect to, now we need, what we need right here is exactly s, right? Similar to this one, if d is symmetric about the line s equals 0, then we need that the function is odd with respect to s. So this is s, this needs to be s. Similarly, if this is s, this needs to be s. So we have the s variable right here. Then we can say that we had 0 for the triple integral. All right, so now we also have similar properties, or if E is symmetric about the plane y equals 0. Or you can say this, the plane SOZ if you want. And also the function is odd with respect to the y variable. Then you can immediately say that the interior is 0. And also, or if, so depending on the situation we have, like in this question, you can say, in this question, you can see that the domain we had E right here is symmetric about the plane Y of Z, right? Y of Z is all right. Y of Z is the plane S equals 0. Is it also symmetric about the plane S of Z, which is the plane Y equals 0? So S equals 0 or Y equals 0 are all right. But the solid right here is not symmetric about the plane S of Y, which is Z equals 0. It's not symmetric about S of Y because you don't see anything below, right? It's not symmetric about S of Y. But anyway, you may consider the corresponding statements right here, and maybe we can get 0. So let me finish this one. So if E is symmetric, this is exactly the plane S of Y, and also F is odd. The Z in these cases, we always have 0 for the interior. So yeah, now let me try to finish question 10, and maybe this is the last question we consider today. Yeah. So question number 10, going back to question number 10. So you can see, I can do like this. All right, so what we are going to evaluate is the triple interior, the function, right? Now, so we can write this in this way. I think I forgot to show you some basis properties, but I think you can basically get it yourself. So we had the following property. Maybe I write it very quickly. And they are from the definition. And they are not new. They are not new because they are similar to the properties we already saw in double interiors. If you consider a triple interior of the sum of two functions, then it's exactly equal to the sum of the corresponding two triple interiors. Yeah, so this is property 1. If you consider the difference, it's still correct. So minus right here, then we have minus right here. Still true for difference. But of course, this is not true for multiplication or division. Yeah, you can see in calculus 1, we didn't have that either. So only for sum or difference. Anyway, so maybe one more property, and then we go to our question. The last one should be if you integrate a function f over some solid E, and let's say the solid E we had is created by two different solids, E1 and E2, then you can write your triple integral as the sum of the function f, the same function f, over E1 and then over E2, and then you take the sum, you get the same for the integral over the whole solid E. So if E consists of E1, E2, then we have this. All right, so now they are very, very understandable properties. So I don't think we need to say much about this. So let's go back to the question. So now you know why we can go from here to here, right? Because of the property I have mentioned. And now we see that this is 0. Why? Because we had two things, right? First, the function, maybe I use the letter Z, is odd with respect to S, right? Do you see that? When you put minus S in here, the output should be minus of what you have S, not minus S. So maybe I just wrote out the definition right here so that if you don't know exactly what a function with the property like this, since z of minus s y z is always equal to minus for any s, any y, any z. That's why we say that this is an odd function with respect to s. This is the definition of an odd function with respect to s. When you put minus into s, and when you don't put minus, then you had two opposite values. For any s, any y, any z, when you had this property, you say that you had an odd function with respect to s. You also had a similar definition for an odd function with respect to y. You only need to put minus y, and then you had the corresponding definition, or you had minus z in here, you have an odd function with respect to z also. All right, so let's see what we have. But this is not enough for this conclusion. We need also the domain, right? So the domain is, sorry, it should be symmetric about the plane. Is that right? But you can look at the picture and you can see that the domain is obviously symmetric about the plane y or z, right? We say the plane s equals 0. This is s, so you should have s equals 0 right here. You cannot have s right here and then y right here. You should have the same if you would like to use the statement. All right, so we have 0 for this one because of this. And now we only need to worry about this, right? Whether we can say that this is 0. Now let's say maybe it's also 0. Now, the function 2z, this is odd with respect to z only. It's not odd with respect to s. You can use the definition and you can see that. This is also not odd with respect to y. It's only odd with respect to z. When it's odd with respect to z, you need to make sure that the domain is symmetric about the plane z equals 0. We see the plane s or y. But you can see the domain we have E right here, it's not symmetric about s or y, right? It's not symmetric about s or y. That's why you cannot say anything for this one. You cannot say that this is 0. Just because you only have one thing, you have that the function is odd with respect to z, but you don't have the property that the domain is symmetric about the plane z equals 0, because it's not true right here. So that's why you cannot say the same thing like we have for the first term, but it's not a real concern because now you can use spherical coordinates. At least you can save time with this one, right? So now you have only this. And then, just use spherical coordinates and handle this one. Now, let me try to finish this question. So you can see now it's from 0 to 2 pi, from 0 to pi over 2, from 0 to radius